Today we want to expand on our idea about a line integral, and we want to upgrade it to a flux integral. In a line integral and a flux integral, we're integrating a vector field. So in both cases, we are integrating a vector field. In a line integral, we're integrating all the vectors in the vector field along a one-dimensional curve. Whereas in a flux integral, we're integrating the vector field at every point on a two-dimensional surface. So the dr and the dA are both parts of the curve and the surface, small parts of the curve and the surface. In the curve, but they are also vectors. In the curve, dr is showing us the direction of the curve at any point. And what we're calculating is the dot product of the vector field at that point and the direction of the curve. And then that's how we're making our calculation. So the dr is showing us the direction of the curve. And at this point, the vector field is, we calculate the vector field is doing some other thing. We calculate the dot product of those two vectors. And that's telling us whatever the dot product can tell us, that's what's going on here. So work is equal to force, say the wind blowing on the bird, times the distance, the direction the bird is trying to go. In a flux integral, we've set the vector field represents something different. We're going to imagine for our flux integral water flowing through a net or a filter. So the word flux is this. It comes from the word flow. So this is a flow integral. We're still integrating a vector field, but this time over a two-dimensional surface. Evaluate this vector field at all these points on the surface. In this case, the dA is going to be a small piece of the surface, but it also needs to be a vector. A vector needs magnitude and direction. Since the dA is going to represent a small piece of the surface, the only direction that makes sense is going to be normal to the surface. Because since it's a surface, there are two vectors that are indicating where the surface goes. So there's one vector that's normal. I guess if we're doing this in 4 dimensions, then we're going to have to adapt this a little bit more. Yeah, let's just stick to 3 for now. So the direction is going to be normal to the surface, and the magnitude of the dA is going to represent the area of the surface. In both a line integral and a flux integral, there has to be some aspect of the dr and the dA going to 0, getting super small. In the dr, remember our line integral goes from t equals a to t equals b. We're just calculating the velocity at more points, so they're getting closer together. In this case, in the case of the flux integral, it's the area of the dA as we chop the surface up into smaller and smaller bits. So let's think about what the flow through a surface can be. We need a basic multiplication on which to expand. The bird flying in the wind, we expanded on work is equal to force times distance. That's a basic multiplication if everything's constant, and it becomes an integral when our factors become variable. So we're going to imagine flow through a surface as the velocity of the water multiplied by the area of the surface, and this will tell us the volume of the water that's going through the surface. If everything is nice and constant, like the velocity of the water is 10 centimeters per second at every point as it hits the surface, and the area of the surface is 5 centimeters, then we get to multiply. Everything is constant, we get to multiply. 10 times 5 is 50 cubic centimeters per second is flowing through the surface. The thing that I didn't mention here is that the water is going at 10 centimeters per second perpendicular to the surface. So those are the two variable things to consider. If things were just this easy, everything was constant all the time, then we can end the problem at 4th grade math. We get to multiply. Because that's how calculus works. If everything is constant, we get to multiply. But this is calculus. So here are the things we need to consider. The velocity might not be constant at every point on the surface, and this is why we're going to have to integrate. Integration is multiplication where one of the factors is variable. So the velocity might not be constant at every point on the surface. The other thing is the vector field might not be hitting the surface perpendicular. If we calculate the vector field at every point on this surface, it's not going to be perpendicular to the surface all the time. So it's going to be, say, at some crazy angle. In which case, if the vector field is at some crazy angle, we don't multiply two constants. We find the dot product of the vector from the vector field and the dA, which is normal to the surface. So we're looking at the dot product of the vector field and a vector normal to the surface at every point. So the vector field is not perpendicular to the surface at every point. That is why we dot product. Any questions? Great. Let's pause here and think of some examples. Maybe talk about this a little bit more. Answer questions. You know, math class stuff. So let's pause the video here and talk about the next thing.